for the second part of section 9.8, we're going to do some more finding the radius of convergence, the interval convergence of our power series. So let's look at the power series. N over n plus 1 times negative 2x to the n minus 1. Go ahead and pause the video, do the ratio test, and see what you get from there. When you've got your stuff worked out at your desk, then go ahead and turn the video back on and see if your steps match mine. The n plus first term over the nth term looks like this, which I can get rid of that now. Here I would go ahead and expand and take negative 2 to the n and x to the n and write these two pieces separately. Same thing here, n minus 1 is what that says. X to the n minus 1 power. When we start reducing, again, of course, the negative sign is not going to be important because of the absolute values there. But I have one more on top. If I take n minus the quantity n minus 1, these guys are going to go away, and I'm just going to be left with one of those on top. So what I have in here, I'm going to have a negative 2, and I'm going to have an x, and then I'm going to have my n plus 1 and n plus 1. N squared plus 2n plus 1. On the bottom, I'm just going to have my n and my n squared, my n and my n plus 2. If we distribute this through, okay, or even because this is considered a constant, if it helps you, you can pull it out in front and just look at what's left. But when I have the same degree, I know I'm going to go to the ratio of the leading coefficients, which in this case is going to be the absolute value of 2x, or I can pull the 2 out if I want to pull it out. I can leave it in or pull it out, but the negative's going to be gone. I know this will converge anytime that expression is less than 1, which means anytime the absolute value of x is less than 1/2, I'm going to converge. So because I'm centered at 0 here, I have my absolute value of x less than 1/2. That tells me the radius of convergence is equal to 1/2 for this example. I'm going to check the endpoints of negative 1/2 and positive 1/2. If I plug in for x, if I plug in negative 1/2 for x, negative 2 times negative 1/2 is 1, minus 1 power. Because the fact that this is not even alternating because it's positive 1, this is just plain old 1 here. N over n plus 1, the nth term test tells us that's going to diverge because that limits 1 instead of 0. If I plug in positive 1/2 for x, then I'm going to have a negative 1 to the n minus 1 power. For the same reason, the alternating series, this one is alternating now because it's negative 1. Alternating series test says if I check my a sub n's, they go to 1 and not 0. So my radius of convergence will be that open interval from negative 1/2 to positive 1/2. Now, if we have a power series centered at C, and we call it f of x, then we know it converges on the interval of radius r. So we could say on the open interval c minus r to c plus r, whatever that radius happens to be, on that open interval it's going to be continuous, and a continuous polynomial is also differentiable. So if I want to take the derivative of a power series, I can do that. I know when I take the derivative, I get to bring the power down when I'm taking the derivative of a polynomial, times the whole thing to the 1 less power, of course, times the derivative of what's inside, which is just going to be a 1. Now, because the derivative of our constant term, our 0 term here, a sub 0, is going to be 0, then we need to adjust the index in our power series. Instead of starting from 0 and going to infinity, we're going to start at 1 now for that derivative. Also, continuous polynomials are integrable as well. So I can integrate f of x dx, and I'll get the sum from n equals 0. And the power rule says raise the power by 1. divide by that power. Constants carry along for the ride. And then, of course, and your book writes this out in front, but then don't forget your plus c. We'll get a constant from that. If I know one or more initial conditions, I can come back and I can figure out what that c is if I need to. When I take the derivative, or if I integrate the power series, my radius of convergence is going to be the same for those two new series, the derivative and the integral. Occasionally, however, the interval of convergence might change. So the endpoints might vary whether they're included or not on the function, its derivative or its integral, depending on the situation. So you still, if you're after the interval of convergence of any of these two new guys, you have to check endpoints. You can't assume that just because this one is or is not included that it'll carry through to the derivative and to the integral.